Okay, so it's freezing in this building. Today we're going to talk about instrumental concepts not covered in 440. So we're going to talk about microscopy. We're going to dig into scanning electron microscopy. We're going to look at X-ray fluorescence and electron spectroscopy for chemical analysis, ESCA. A lot of times the acronym ESCA is not used, but it's a similar thing to what we do on electron microscopes, where we have wavelength dispersive spectroscopy or energy dispersive spectroscopy. So we'll get into those other things that are used in not just in forensics, but also in a lot of material science labs. So scanning electron microscopy is a very, very good technique for trace analysis. And so this is, again, we want to really look at microscopy. We have modern microscopy like the electron microscopy, but we still use old school microscopy. And that's a historical method that's been used in forensic science. So the question why? What do you think? Why would we still use something that's ancient and has been replaced with all of these? Why hasn't it been replaced with all of these fancy new instruments like GCMS and liquid chromatography, time of flight mass spectrometry, and all of these really fancy techniques? Why would we keep something ancient like regular visible microscopy? Yes, it's very inexpensive. Microscopes, just optical microscopes. I mean, you may think they're kind of expensive if you go look at the catalog, but but in terms compared to not just the instrument, but the maintenance costs and the staffing for these modern instruments, it's much less expensive. And also it's historical. We know these techniques are tried and true, and we know we have a lot of good training on how to identify certain kinds of plants, certain kinds of objects. There's microcrystalline tests we can do on certain drugs and so on. They react with certain reagents and make certain shaped crystals, and we're like, yes, absolutely, that's cocaine. So there's a microcrystalline test for cocaine. Put it with a reagent, it produces crystals of a certain shape. You look under the microscope, there you go. Now, you haven't actually chemically analyzed it as cocaine. It's consistent with cocaine. You can't say positive that it's identified as cocaine, but it's another checkbox. And then you could take that sample and send it to a confirmatory test like a FTIR or mass spectrometry. So microscopes, optical microscopes, deal with refraction of light. And if you've ever seen, have you ever have a glass of water and you put a straw in there and it looks broken? Have you ever done that? It's really fun. You can do it with your fingers too. Do your swimming pool, And anyway, it looks broken because the refraction of light in water is bent quite a bit more, because this angle here depends upon the refractive indices. So we have the angle in air, the angle in water, and we have the sign of those angles, and then we have the refractive indices here of glass and of air. And so you can see that as we're going in, this incident light comes in, it strikes this surface at a certain angle with the normal. Oops, I can't spell. So they say that line is normal to the surface. It's 90 degrees to the surface. Okay. And so this angle of incidence is with respect to the normal incidence. It hits, and then the glass is inside, this angle with the glass is inside the normal, inside the glass. And so then it bends, and then when it comes out, it bends even more in the same direction. So the original path is here. And so like if you're looking at your finger, it's above the water, it's not bent much through air and through the glass, and then inside the water it's way over here because of the way it's bent. So next time you're at home and you have a glass, stick a pencil or a piece of a straw or something, you can see some fun stuff. So we can use this to direct light, to focus it, to defocus it, to collimate it, to control it. And so that's what a microscope is based upon. So this is a very simple version of a microscope. This has only got 4 optical elements in it. Many of them are more complicated than this, but this is a decent image of what's going on inside the microscope. So we have down here the object plane. This is what you're viewing with the microscope. So you got this tiny little arrow here, Okay, it goes through and you can trace the rays of all of the different, like the arrow tip, is this image is focused on that spot. You can follow the red images. And here you have this intermediate image where it shows up upside down. It's a little bit bigger. And then it goes in through the eye loop, and then it shows up over here magnified. You see it's gotten larger. And so then what we have is this blue region is right here in the microscope. So that's the bottom part of the microscope, taking into account the object plane, which is down there on the stage, going through the objective, internal optics. There's a little mirror that bends it, sends it to the eye. And then this last part is the green piece, which is the eyepiece. And then the image plane is either your retina or camera or some other kind of optical capturing device. Okay. And so the total magnification of this is the product. So these numbers are multiplied by each other. So if you have an objective lens here, this one says a 40 on there. So it's a 40x objective. Here's a 60x and here's a 100x. There's not much difference in their dimension, but you can look at the lenses. They look quite a bit different. Okay. And so 40, 60, 100. So this 41, and then we might have an eyepiece. If you look on the top of the microscope, you'll see the magnification of the eyepiece, and that's a 10x eyepiece here. Then overall, it's a 400x magnification. So you got to know the objective and the eyepiece. Many times you just pick the eyepieces, like a 10x eyepiece, and then you rotate this nose here and go from 40 to 60 to 100, and you can look at it that way. How many of you, I know y'all are forensic chemistry majors, but any of your, have you had biology or have you used microscopes? So it looks like, yeah. How much detail did they go into in terms of selecting objectives and all of that? What'd they say? Just switch it, yeah, go to 40x or whatever, yeah, okay. Did y'all do oil immersion? You did, okay, that's good. Did you use with a cover slip or without? With, yeah, it makes it more stable. You disperse the sample under the cover slip, then you put a drop of oil, and then you bring the nose of the eyepiece in. Yeah. Okay. So this is the effects of the objective and the numerical aperture and the resolving power. So here, this numerical aperture is also written on the objective. You can see them right here: 0.65, 0.85, 1.25 in oil, 0.17 in air. And so that's that numerical aperture. You could calculate it if you knew the geometry of the aperture. So this is the angle, the aperture angle. So it's this angle right here, theta over or phi over 2. Take the sine, and then the refractive index of the gap. And the reason we want to use oil, we'll see in a minute. We change that refractive index and we increase the numerical aperture. Okay, and that makes our resolving power small. So the resolving power is sort of like the smallest objects you can tell apart. Like how close could two lines be before you could see light between them? Okay. So this is some of the calculations you'll have for the homework. It's using this, and then this is the wavelength of light you're using. Okay, so this is good to know if you're, from the blue end of the spectrum, 400 nanometers, to the red end of the spectrum, 700. So these are the ranges that you'll use. A lot of times they'll use 589. It's kind of right in the middle, but it's also a very recognizable light, and it's also very simple light to produce. Does anybody know what 589? Why that's a weird number to just pull out of your head. What's special about 589? Okay, good. Trivia, right? Next time you're at the bar and they have trivia, they ask you, what element produces light at 589 nanometers? Sodium. Okay, sodium lamp. Okay, it's a very inexpensive lamp, and it's that yellow light. Sometimes you see on street lights, the yellow street lights, the sodium vapor lamp. Just like we have mercury vapor lamps in all of our fluorescent tubes and so on, the sodium's even cheaper than that. And so they have sodium lamps. So that 589 is a good number to use. It's right in the middle of the visible range. But if you want the smallest possible, if you were using blue light, that would be the smallest resolving power. And so here's an example of the resolving power. We're using 550 here. And we have an oil immersion lens with a 1.3 numerical aperture. And so this would be the resolving power. So in a perfect situation, if you had, really close lines, you could see light between them. That would be the diffraction limit, right? If you were using this in air, so, this is an oil immersion lens, but let's say you didn't have the oil, you were just doing it quickly, your resolving power would suffer. See, it's not as bright, not as good. Seeing the difference between these two objects, where one object ends and the other one begins. Okay. Now, what kind of oils do we have? Well, look at all of this selection here. I mean, water is 1.3 refractive index, glycerin 1.4695. I mean, these are very specific. Paraffin 1.48, cedar wood 1.5. You can make synthetic oil that matches that. Then you get into the bromines and iodines. And with the big ball of electrons, what's going on with refractive index is it's how much the light slows down in the medium. So think about light going in a vacuum. Okay, that's the fastest light can go. So 299792458 meters per second. I know that because it's a cheat code in one of my games. Okay, but that's the speed of light. It's for fast building. So 299792458 meters per second in a vacuum. When it hits air, it slows down. How much? Well, 1 over 1.0003, so not much. It doesn't slow down much in air. It hits water, now it slows down by a factor of 1 over 1.3. So it slows down a pretty big amount, okay? And that also causes it to bend more. So when it hits the big, and it's the electrons. Think about light. It's an oscillating electric field. And we did the whole red ball hydrogen atom thing. And so this cloud of electrons around every atom, think about the cloud of electrons around an iodine. Iodine has 53 protons. And so there's 53 electrons around iodine. And when light comes in, it's like walking through Jello. Okay. It's interacting with all of those charged particles. And you could think of it as instantaneous absorptions and re-emissions. So the electron starts to oscillate, and then it stops oscillating and spits out the photon of light again. And then it hits another electron, which oscillates, and then it spits out the photon again. So it's quadrillions of absorptions and re-emissions is a way to think about it. Okay, but it's not really a good analogy that there's no energy level where the electron can hop to if you're not on a transition wavelength. So it's really like a virtual level, kind of like Raman scattering. We have the dashed line at the top. It oscillates with the electric field and then scatters it off. Okay, so if it scatters off at an angle, we call it Rayleigh scattering. So light comes in, it's oscillating, interacts with an electron, it goes this way. That's Rayleigh scattering because the wavelength of the light hasn't changed. But what if light comes in, oscillates with the electrons, and goes again in the same direction? That's refractive index. So it's the same direction. If it was a different direction, it'd be scattering. It's bounced off. But if it's in the same direction, it's refractive index. And most of the light continues in the same direction. A lot of light is scattered, and very little, like 1 in a billion chance, you might have a Raman transition. So Raman is really, really small, but it's the same phenomenon. Light interacting with the electron cloud, and either inelastic scattering, inelastic, which is Raman, elastic scattering, which is Rayleigh, or continuing in the same path, which is refractive index. Now, the fun thing about this, we just said that light is bent. It bends when it hits a material. So and it hits when it hits a material that has a different refractive index. So in a microscope, how is it that we see the edges of something? So let me draw two particular situations. We've got the field of view here. And let's say we want to take a picture of a glass fragment that was found at a crime scene. And so we've got a glass fragment that looks like this, okay? Okay, so that's our glass fragment. We get a picture of it. We can see the outline of it. Why? Well, because when light is going through the glass, it goes at a different speed than light that's going through air. Okay? And so we can see the edges. Right at the edge, some of that light is bent into the glass and some of it goes past in the air. So the edges are viewable only because there's a refractive index difference between the air and the glass. Maybe we put it in oil. We still see the edge if there's a refractive index difference between the oil and the glass. But what if we put it in an oil that matches? So this is an old school technique. You've got your field of view and trying exactly the same picture. And we put it in paraffin oil. Okay. And so we have glass, maybe we have air, maybe we have water, you know, and this might take some tedious, and then glycerin. But then when we get to paraffin oil, our little glass disappears. Why? Where'd it go? It's still there, but we don't see the edges because it has exactly the same refractive index as paraffin oil. So now we've got a data point on our glass. And then if you have that's maybe on the victim, and then you have something from the car that you think they hit them with, and you can look and say, well, these two pieces of glass have the same refractive index or not. You know, if it's not, then it's exculpatory. If it is, it's inclusive. And you can make a decision based on the refractive index of the glass. So this is a way to get a refractive index of a tiny little chip of material. If you can match it, and that's why we have these purified oils. You can buy a kit of all of these different oils, and you can use them to index match, typically done with something clear, right? Because you can see through it when the oil matches, and typically done with glass. So that's old school. Okay. And so we got some calculations here, but this is sort of what's happening with the resolving power. It was 254. You use air, it's 385. Not nearly as good. Okay. So smaller resolving power is better because you can resolve smaller objects. Okay. Now let's look at polarized light microscopy. This is so fun. Okay. So if we have an isotropic specimen, and one way to think of isotropic is you've got refractive indices that go in certain directions. Why are these pens are not behaving? Okay, you've got a refractive index in the x direction and a refractive index in the y direction. And isotropic in x equals in y. And anisotropic for both of these, in x does not equal in y. If that's the case, it will rotate plane polarized light. Now, why might a material have a different refractive index based upon the angle in the material? Well, crystals. Think about how crystals are. Let's just take a molecule like benzene and stack them. So we got flat benzene here stacked on top of flat benzene. And so we've got sheets. So light going through the sheet this way will probably slow down differently than light going through it this way. And so that would be an anisotropic material, the way it's crystallized. Now maybe we have benzene in a certain pattern, it's T-shaped. And so T-shaped benzene may be isotropic, but there may be a solid benzene in a certain way where it's anisotropic. And so this would tell you something about the crystal, something about the material. The way you would tell is using cross-polarized microscopy. So look at my fingers on the video. You can see them going this way. You see how they cross each other. And so fingers this way would let light through these slits. So vertically polarized light could come through here. If I have another polarizer, horizontally polarized light could get through here. If I cross them, no light gets through, because this lets vertically polarized light through, and that's blocked by this one. So if we have an isotropic sample, and I had the polarizers crossed, you see this has got an arrow this way, that has an arrow going forward and backwards, and I have my sample in here, and unpolarized light goes to the first polarizer, now it's polarized this way, goes to the sample, look, it's not rotated. Same thing, it hits that next polarizer and it's completely blocked. And so the field of view is black. So I'm looking through the microscope, and I've got my sample there, and I don't see anything. Well, first of all, I would move one of the polarizers and I would get the sample in focus. All right, and then I put the polarizer back, and then I don't see anything, and I was like, okay, this is an isotropic sample. It's not rotating the plane polarized light. Okay. Now, if you happen to line it up a certain way with the anisotropic specimen, you may still get a black screen, but if you rotate the specimen, it can show up. Okay. And so since it's rotating light, it will get through the second polarizer. But light that comes around the outside of the specimen isn't rotated at all because it's not going through anything. So light out here that misses the sample shows up as black. Light that hits the sample and is rotated can now make it through the second analyzer, and you see light in your objective or on your camera or in your eye. So here's some pictures from my lab of some crystallization studies that I did. And you can see the black background. See, this is light that didn't go through a sample, and so the cross polarizers are blocking it. And then the light that does go through the sample is being rotated, and it does make it through the second analyzer. Now, it's also pretty cool that you get pretty pictures. I love this one right here. The wavelengths of light have different frequencies, and as they go through the sample, they have they turn more, and so you get different colors based on the thickness of the sample. So the thickness of the sample is what's giving us different colors. So this is a crystal that was precipitated. It's an organic substance. It's nitroaniline. It was dissolved in like DMSO or N-methylpyrrolidone. And then from there, it was put into, I think these are methanol, and then from methanol to water. So it crash precipitated it out in water from methanol, from NMP. And I was trying to see if the intermediate solvent made a difference, and it did. So it was a successful project. But look right here, you've got this funny looking crystal, and you've got a green patch in the middle. This crystal was formed, it was making a nice like flat crystal, but there was a pit in it where it still had some solvent. And then eventually the solvent evaporated away and left this little pit. It's kind of like a little swimming pool in that crystal. Whoa, that's tablet. Okay, and so what we're seeing is different depths. So this little pit is a dip in that crystal, and you can see it. Okay, here's a crystal. There's like a chip here. So this is like stairs right here, and then a smaller little patio out there. Okay, or it could be coming at us. This could be a rise, and it could be a higher spot than the other. You can't really tell from the color which one's lower and which one's higher, because the light will turn around and say green would come out, and then it would turn around more and red would come out. But if it keeps going around even higher, green will come out again, and then red will come out again. All the colors of the rainbow will come out, but they'll come out in order. So it depends on if one is slightly below, it might be red and green. But if this one is far enough up, it might be red and this might be green. So you really can't tell the depth perception. You can just say they're different depths. But you can't say that red is always below green or green is always above red, because it's a circular path, like a spiral staircase. And so it's going through the whole rainbow all the way up the stairs in depth. And so these light paths are turning through this anisotropic crystal, going around, and whenever the spiral staircase hits the surface, it comes out, and you've got that color of light. Okay. It's the same thing that happens in a grating, but this is a volume grating. So we're getting diffraction of light based on the thickness of the grating, not on the dispersion with the lines. So in instrumental, you had gratings, and it was angle dependent based upon the lines that it hit. You can take those lines and turn them sideways, and you have a volume grating. It's the spiral staircase going through the grating, and depending on the thickness of the grating, you get the different colors. So let's look at some of the basic spectroscopic terms. Starting to warm up. Arms are thawed. This one, I mean, you should be very familiar with absorbance and transmittance. It's always nice to review, though. So our incident light comes in. So we have I0, and we have I here. And the ratio is transmittance. Okay. And then that's equal to 10 to the minus A, which is absorbance. Yeah. So that's given right here, absorbance. And A is the minus log of T, or EBC. This is the absorptivity. B is the path length. And C is the concentration. Okay. The biggest take-home lesson here is that absorbance, A, is directly proportional to the concentration. And of course the path length too. But that's where we get our calibration curves. We change the concentration and we get this linear change in absorbance values. If we need a more sensitive instrument, we increase the path length if we can, right? And we do that in our research lab. You know, we can have little tiny path lengths, and we can have really long ones. Okay, and then we have just talked about the scattering. We did the Rayleigh scattering. Golly, touch this thing the wrong way, it goes berserk. So we have this Rayleigh and Raman scattering, and then we have reflection. So reflection is shown down here, and this is an area that we didn't really cover much, I don't think, in instrumental, but the two different types of reflection. Okay, so we have specular reflectance, and this is the main point right here. It's angle, it preserves the angle. Preserves the angle of incidence. And then diffuse reflectance is all other angles. All other thetas if you want. And so one of these gives you information about the color of the substance that's reflecting the light, and it's the diffuse. But this one is where we experience color. And I'm speaking in general terms, but color. Color of object. This specular reflectance will give you color too, but it's, I'll say, the color of the source. And you can see this, let me see. You could see what I see. When I look at this black surface, I'm looking at, it's clearly a black surface, right? But when I look and I can kind of see the reflection of the lights, it looks whiter. Why? It's white because the light is white, not the surface. At all other angles, the surface is black. But when I get to the specular reflectance of the light, preserving that angle of incidence, I'm looking at the source. If this surface was smoother, then I would really get like an image of the source if it was smooth. So the rougher the surface, so the diffuse reflectance gives the color of the object and roughness. So the more rough the surface is, the more diffuse reflectance I have. The more mirror-like or smooth the surface, the more specular reflectance I have. And then total reflectance is the sum of those. So you can get a detector that's dumb and it just looks and takes in light, and you get the total reflectance, and then you block the angle of the source and it has to come at some other angle, then you get the color of the surface. So you can get total, you get diffuse, and then to subtract the two, you get specular. Yeah. So that's how specular is typically measured. We measure total, and then we block the source angle to the detector, and we get the diffuse, and the difference is the specular. Now this internal reflectance, this can have some fun effects. We can match these layers. We can have certain paint layers. So this is important for paint. How many people have seen these cars that drive by and they change color as they go by? It's this really sweet paint job, and it's got some clear layers, and it's angle dependent because this path through those clear layers is going to be sort of that anisotropic thing. It's going to give a certain color out, and if it takes a different angle, it'll reinforce a different color. I've seen orange and purple. I've seen this paint job that goes from orange to purple. It's really crazy looking. You see an orange car, and as it drives by, there's certain angles at which it's purple, and then it turns orange again as it goes away. So it's just a really slick paint job. Can't imagine how much that costs. But that would be very forensically relevant, right? If you had a very specific paint chip, you're like, okay, this thing is crazy. I look at it in a microscope, and you need a tilting stage probably. Okay, then let's look at different instruments too. I don't know how much, I know y'all do block diagrams and instrumental, and you probably talked about dispersive and diode array instruments. So let's look at these again real quick. So these are both dispersive instruments, but one has a fixed grating and a diode array. So this right here is a diode array. These are low power, really cheap, super cheap now. The expense comes in the high resolution. You just get a more high resolution diode. But we've made digital cameras so ubiquitous that now we can just use one of those camera elements in a spectrometer. And so that's why these spectrometers have come down in cost. They even make some that are as small as a USB drive that will just stick right in your laptop. So, that's something we can look forward to in the future. We can take the evident, take spectra right there, reflectance spectra right there at the crime scene. And that's kind of nice. In terms of chain of custody, it was straight from the scene. I mean, there's no ambiguity, right? Now, a little bit more sensitive, you could get a photomultiplier tube, which can count single photons, believe it or not. So, and these are more sensitive, so you can get more, smaller samples, trace amounts of light in those. The problem with both of these is that higher resolution requires narrow slits in both cases. Why is that a problem? If we want high resolution from a dispersive instrument, what do we have to do? We have to narrow the slits. So when we narrow the slits, what does that do to us? How does that hurt us? The slits are letting light into the instrument. So what happens if I crank them down? much less light. So higher resolution, you're losing your signal to noise. You're losing all of your signal. And then you get down into the noise level. So the narrower your slit, yeah, you increase the resolution, but you're losing your light. Okay, so you have to look longer. So it slows things down. And then also in the scanning one here, high resolution requires slow scan. So you just got to really creep along a tenth of a nanometer at a time and let that photomultiplier tube stare into the darkness, and maybe it'll see some light from your sample. Okay. But the whole time it's doing that, the thermal photons in the room are creating false signals. And so you got a large amount of noise. And so it's just a limit. There's a limit to the resolution of dispersive instruments. And so that's why we went to Fourier transform instruments. And so this is how we measure the resolution, is full width at half maximum. This idea of resolving power, it's that lambda over delta lambda, and that uncertainty or delta lambda is the full width at half maximum. So if we have a spectral peak, we go halfway down from the maximum and we take the full width. That's what FWHM is. That's a good measure of our resolution. And so we typically think of Gaussian peak shapes. And so this is, Gaussian peak shapes, we use sigma to determine the width of those Gaussians, but sigma is not the full width at half maximum. This is the relationship. And if you're a math person, this is a fun derivation. So you can go from this Gaussian equation and see where I got this. And you'll get a sticker if you do that. Okay. So it's not sigma, it's really 2 times sigma, but it's a little bigger than 2 times sigma. So sigma is right about here. It's not halfway down. Sigma is not quite halfway down. So you have to expand sigma a little bit, okay? Times the square root of 2 times the natural log of 2, okay? Oh, sigma is actually the inflection point. What is an inflection point? Look at the slope. This slope is going down. It's curving down, and sometime later it starts to curve up. It's where it goes from curving down to curving up. That's the inflection point. So somewhere on that curve, the curve stops curving down and starts to curve the other direction. That's sigma. That's where it shows up. It's not halfway down. That would be the full width at half max. So that's that. So now we have this resolution. We want to get high resolution. We narrow our slits. We get noise, we lose our signal, and so then we have to correct that with Fourier transform instruments. Another thing that happens when our scans go a long time is we end up with drift. So our spectrometer drifts. And did y'all have good luck with the Spec 20s? You did the Spec 20 experiments in Gen Chem? I see some sour faces. Do you remember the Spec 20? It's a little box, looked like a shoebox, and you had one little hole in there, and you put in your water, and you measure it to 0, right? And then you set it aside and you do your test tubes and you put them each in at one time. Okay, what happens? You measure your blank, okay? And you're using your source, goes through your blank, hits the detector, you set that to 0 absorbance. You pull your blank out, you put your sample in, and somebody gets in the elevator. What does that do? Drains the power grid and your source gets dimmer. And your absorbance on your sample, since the detector sees less light, says, oh, this absorbance is high. It's not. I mean, it's somewhat high, but it's even higher because the light went down. It got dimmer because of the elevator. That's drift. Okay, so your spectrometer in a single beam thing where you got a single beam, you put the reference in, adjust it, take it out, someone gets in the elevator, you put your sample in, the dimmer light source is misinterpreted as a higher absorbance, okay, or lower. Maybe your blank is in there while somebody's coming up to the 3rd floor. You take it out, the beam gets brighter, you stick your sample in, and now your absorbance is lower than you expected. So on your calibration curve with a drifty instrument, it's got points that are up and down in bad ways. Okay, there are other things too that can cause trouble with drift. So this is a way to get rid of that drift. Go real fast and make a bunch of measurements. Okay, now that's not going to be good. You're going to spill your liquids. Okay, so don't move the samples, move the beam. And that's what the chopper does. It's up there, that rotating mirror sends the reference, then the sample, then the reference, then the sample to the detector. And you get a really ugly signal. You get this chopped signal. So, come on. So I made this thing. This right here is, I mean, let's just forget that. Okay, I put this in here. So this is more of what it looks like. Look at the drift. So this is the drift of the source. You see how it's drifting all over the place? Okay. So here the elevator starts, right? Elevator starts going up. And then here it reaches the floor, you know, and it has to stop. So the motor drains a little bit. And now the elevator is gone, is stopped. And so the source is as bright as it can be. Okay. And then during that time, we've chopped the sample cell in there. You know, we put it in and it's kind of bouncing around and then it stabilizes. And so we get a measurement of I when the chopper is sending it through the reference, or through the sample, and we get an I naught when it's sending it through the reference cell. And it's tick, 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 tick. And we tell the computer, take the average of the I naughts and the I's and get a nice stable ratio. Okay. So that's what we would have. Now this chop frequency, rotating segment, choose frequency wisely. Any multiple of 60 hertz in the USA. Oddly specific, isn't it? So that means don't run your chopper to where I and I naught are coming in at 60 times a second, or 120 times a second, or 360 times a second, or 1,200 times a second. You can chop these pretty quickly. What's going on at 60 hertz in the United States? Not radio. That's a good question. Our FM bands are in the megahertz. Okay, so you'd want to avoid those too. You wouldn't want to run it. In Huntsville, we don't have a lot of choices. What's our radio station? 100.7 KSAM? I think it's one. Don't quote me, but it's around 100 megahertz. So you would want to avoid that too. So something's going on with the interferences, right? But y'all got to know what 60 hertz is. So you got to know that. It's like basic science knowledge. In Europe, it'd be 50 hertz in Europe. So avoid that. What is it? What? Light bulb? It's related to the light bulbs. This whole building is bouncing at 60 hertz. Like you can't feel it, but it's like, huh? No, it's an analogy, I guess, or metaphor. It's not really, it's bouncing, but electrically it's bouncing. Huh? What? No, not the sun. No, yeah, this guy's right here. The whole building is surrounded by wires all through the walls going up and down at 60 hertz electrically. And if your chopper's going at 60 hertz and you're trying to get I and I naught at 60 hertz, it's going to interfere with that. It's going to go berserk. And you will know it because your signal will be crazy. At some time it tries to get I and it's at a low point at 60 hertz and then I naught is up above and then other times they're reversed. And your spectrum is just going to be noise, but enormous noise. And you're like, my spectrometer's broken. No, well, maybe the motor on your chopper's broken and it's running at 60 hertz. It needs to run at a frequency that has nothing to do with 60 hertz, not 120, not 180, not 360, none of those frequencies, because all of them will have some interference that will destroy your signal, because the interference will be greatly larger than your signal. So anyway, that's a little pro tip. Now we can get away from the high resolution slits and narrowing our sample down by going to interferometry. So this is a really bizarre thing. There's no slits, and 100% of the light is being used. So this is the big advantage of FT instruments, like FTIR. They even have FT UV vis. It's not common, but they have it. Okay. And resolution is just governed by the length of this moving mirror. So the light comes in, so that we've got the infrared source, it's coming in here. It hits, let's see, do I have, yeah, okay. And so it's split 50-50. So 50% goes up and 50% goes through. So how do they do that? Well, they have a salt window, and they've perfected the process of sputtering a little bit of aluminum on there, or mylar, or some kind of metal that's going to reflect the light. They could make it a perfect mirror, and then 100% would reflect. So they just sputter a little bit, and they get 50-50. Okay? That's just their technology, right? They figure it out. If we run this sputterer for 20 seconds, we get 50-50. 21 seconds, it's not. It's like 51-49. Okay, so they've perfected the way to make these beam splitters so that half the light is reflected, the other half goes through, statistically. So that's pretty nice. Then they hit these cube mirrors. Have you ever been in a bathroom where the mirrors meet in the corner? You can't get out of the corner. Have you ever noticed that? You will now, right? No matter where you are in a room, you're looking at the corner, and the split's going to be right here, and you're going to have one eye on either side of that corner. Because the light, what you're looking at is your reflection, so your eyes are going there, and they're hitting that corner, swapping places and coming right back, no matter what angle you're at. So if it's misaligned at all, this is kind of cool. If let's say we were coming at this angle, it comes along here, it glances this one, bing, and it hits this one sharply and comes right back on a parallel path. So these two lines are always parallel. I can't draw the 3D version of this, but a cube will do the same thing. A corner cube where you have three mirrors all at right angles. You'll never get out of the corner of that cube. No matter what angle you're coming at, it always comes back parallel to that. And so when you're looking in the mirror and you've got the two mirrors next to each other, whatever angle you're at, it comes back parallel. And so that's why you can't get out of the corner when those two mirrors meet. This is just a great way to make sure that whatever light hits that mirror comes straight back in a parallel path. So it's kind of setting up a resonant cavity. This is also how we put our reflectors up on the moon to measure the distance of the moon over time. We put big cube reflectors and we shoot lasers at the moon. And even, can you imagine how bad that would be? Like they get this plane mirror on the moon and it's angled slightly off. So like we hit it, it shoots off and we never see it again. But no, they put a cube mirror, so no matter what angle we're at from the Earth, it hits that cube mirror and comes back to the parallel path. And then we shoot a pulse, and we wait, gets to the moon, comes back, and we're like, okay, the moon has moved away slightly or moved towards us slightly. We're not measuring the speed of light, that's defined. We're measuring the distance to the moon. And it does change this slight amount. I can't remember if it's getting closer or moving away.
It's going away.
It's going away. Okay, thanks. Yeah. So trivia. That's good. Okay, so 50-50. Yes. Let's see. What length do we need for 4 centimeters? Yeah, this might be the case. Oh no, this is what we need for 2.5, right? So this is 0.04, 1 over 0.4. Yeah. So yeah, this might be a typo here. But you could use this equation to calculate what it would be for four-way number. So before we get to that, though, let's look again. So 50% goes up, it returns. This is a fully silvered mirror, so 50% comes back. And then miraculously, at least in my mind, 100% comes out. That's so weird to me. It's not, nothing's lost. So the 100% goes in, it splits, comes back, and recombines, and 100% comes out. And the way to think about this is it's a resonant cavity. Like the whole thing's behaving as a resonator. Okay. Now, if we move one of these mirrors, some wavelengths are going to interfere with each other, and they're not going to come out. So we can use this to scan through different wavelengths of light by moving that mirror. Now, if we move it a little bit, not very many wavelengths are going to be canceled out. If we move it a lot, then the different paths, if wavelengths are really close to each other, let's say they only differ by one is 100 waves per centimeter, and the other one is 101 waves per centimeter. Very close together, right? And so we would have to move that, let's just say 100, so that this one goes 101, and this one goes 100, and then it comes down, this one goes 101 again, and this goes 100. They're going to be out of phase at a certain distance, and they'll cancel each other out. But trying to determine between 100 and 101 is going to take a longer distance than trying to determine between 100 and 50. Okay, so that's where this resolution equation comes from. So it's this the uncertainty, or the difference between these wave number values, is 1/2 times the maximum distance. Okay. So this is what we have in our spectrometers. This is the one in DW's lab, in my lab. We've got the interferometer here, and it's pretty small. It moves both mirrors on a little rocker arm, and it might move. Maybe the whole length is probably 4 or 5 centimeters. Okay, it's not very far. In my research in graduate school, we wanted to get 1,000th of a wave number resolution. So we wanted 0.001 wave number resolution. We were doing molecular spectroscopy in the gas phase, and we wanted to resolve a rotational line. And so we went to Pacific Northwest Laboratories, where they had an interferometer spectrometer similar to this, but instead of a tiny interferometer, it had this big old beast with a 5-meter mirror movement. And so the spectrometer was like this big, but the interferometer went clear across the room, and it had like a shuttle and a little cable that pulled it, and it moved. It took forever to get data on that thing, but it was great. This is a really interesting spectrometer because it's got lots of places where you can put attachments. Like we have a microscope on here, but you could have other kinds of detectors. It's very versatile. And here's the microscope that we have, this infrared microscope. So this is pretty cool. It does visible and infrared microscopy. So it's got a visible lamp for reflectance, where it comes from the top and hits the sample. It's got a visible lamp for transmission, where it comes from the bottom. You can send the infrared beam up to the top and do infrared from the top. You can send the infrared beam down to the bottom and go through the sample. And then it comes up here and it splits over to the detector. You could have multiple detectors. It can go to the video. You can get an image, video or static, and then it goes to your eye. Okay. And then it also has polarizers. So we could do the cross polarizers on the top and the bottom. So it's a fantastic piece of equipment. The sad part is this mirror that switches from reflectance to transmission back here on the back, it's broke. So I need a tip jar so people can speak. We need to get that fixed. Okay, now for the sample part. So infrared, we could do reflectance, we could do transmission, but we have this new attachment, somewhat new, been around 20 or so years, the attenuated total reflection. So let's break this word apart. We're talking about reflection, and so we have this reflection here, and that's the total part, total reflection, 100% reflected. But the sample's on the other side. This is a diamond. There are other substances, but we like diamond in education because it's, don't take this personally, it's student proof. Right? So, you can scrape it, you can stick glue on there, pop it off, whatever. I mean, it's a robust thing. It's harder than any of the other substances, so you're not going to scratch the diamond, okay? Zinc selenide is softer, and it gets scratched up. Okay, and then we can press the sample onto this diamond and get a good spectrum. Now, when the sample is pressed onto the diamond, we can have attenuation. So this attenuation, that is another word for reduced. So it's total reflection that's reduced at certain frequencies. I'll just do the little wave number thing. And how does this work? Well, it's total reflection, so it's an evanescent wave. It's a wave that extends into a region where it cannot propagate. So the light is bouncing off the inner surface of that diamond because of the giant refractive index change. So diamond has a really high refractive index. So it's hitting that and it's bouncing, and we pick the angle where 100% bounces back. Okay, but where that edge of the diamond is, it's bouncing like a trampoline. So this is what's happening right there where the sample is. Okay, the light's not going through, but it's interacting. So the trampoline is the top of the diamond, and your sample is the cat and the kid. Okay, and your sample has different frequencies. And so you see the cat is about twice the frequency as the kid. Okay, so whatever the cat frequency is, we would have attenuation. And whatever the kid frequency is, we'd have attenuation. And so then you get a spectrum, and you look up at your little correlation chart. It's like, oh, we got one kid and one cat on our diamond. Okay. And so that's what's happening. It could be a CH stretch. It could be a carbonyl. It could be the whole molecule bending. Okay, so, you know, the whole normal mode vibrational analysis. The downside of attenuated total reflectance is that the path length, this interaction depth, the bounciness of the trampoline, is a function of the x-axis, the frequency. So over here at 500, you see this curved line is the penetration depth. So over here at 500, it's about 1.3 microns. So it's going pretty far into the sample. But over here at 3000, where the CH stretch region is, it's only 0.2 microns. So that's your path length. And remember, absorbance is proportional to path length. So if your path length is super small, you're not going to get very much signal. So the CH peaks are shrunk, and these down here are really expanded and are larger. And because it's a sloping penetration, your peaks are shifted a little bit. If 1400, if this peak was transmission, and you got, say this is cocaine sample, whatever, 1400, you put it in the ATR, it shows up at 1390. And so that's where originally this faced some obstacle in court, because the libraries were all transmission libraries, but then when they wanted to use the new sampling technique of the ATR, all their peaks were shifted a little bit. And they're like, well, you said cocaine was 1400, and your peak says 1390. Those aren't the same, are they? You know, and so there was some challenges, but they fixed all that. They went and redid all of the libraries with the ATR. So that's a good principle. If you're going to use a technique, a sampling technique, your library and your samples need to be using the same technique. So you can't have a library of transmission spectra and compare your ATR spectra to a transmission library. I mean, it'll get you close, but you might face a challenge. So it's best to use your sample technique to match your library technique. And it was a moneymaker for whoever made the libraries. Let's look at some of the other spectroscopic techniques. I think I'm going to kind of rely that UV vis, flame AA, the basics of FTIR and Raman were covered well in 4440. So let's look at X-ray fluorescence, scanning electron microscopy, and this ESCA. So here's what's going on with X-ray fluorescence. We like to tune this. We like to pound it with a high energy X-ray. So we're knocking out core electrons. For certain materials, typically we ignore rows 1 and 2. So beginning with row 3 of the periodic table, that's the information we're going to get. Now that's disappointing if you want to get something about carbon, nitrogen, oxygen, and fluorine. But those are just ubiquitous. They're everywhere. So you couldn't really tell if it was just background carbon from our pine trees or if it was from your sample. So carbon is everywhere. So a lot of times we don't even look at carbon for X-ray fluorescence. We're looking at third row or greater. And so when we knock out this 1s electron here, we've got a, you know, it's like musical chairs in the atom. We've got some chairs down here. These are supposed to be chairs. And the music stops, and all of these, you know, 2p electrons and maybe a 3p electron jump down into the 1s. And as they jump that far energetically, they spit out X-rays. So this is X-ray fluorescence. We hit it with a high energy X-ray, and we get red-shifted X-rays out. Okay. This can also penetrate pretty deeply in a material too. So like they can shoot these X-rays into diesel and get the signal for sulfur. So it's a very sensitive technique for trace amounts of sulfur. Now, this can happen from using electrons too. So instead of using X-rays, we can spit electrons. Electrons can knock out 1s electrons too. So this is a way to get X-ray photons from an electron microscope. So if these electrons knock out 1s electrons, we'll get X-ray photons out. Now this is a microscope too, which is kind of bizarre that we can treat electrons like light, but they're charged particles, and we can use various amounts of charges on these little plates here, you know, high voltage or low voltage or whatever, and we can steer the beam, we can shrink the beam, we can expand the beam. So we can control the beam of electrons just like lenses control the beam of light. So these are called electronic lenses. I'll put it in quotes. So we're using those little rings, and we charge those rings up at different voltages, and we can tighten or expand the electron beam. We can also steer it left and right. And we can hit certain places on our sample and get backscattered electrons. So you need to raster the beam. And so this is the term. Do you remember in old TVs? This is what they did. This is like a cathode ray where they would shoot an electron beam at the TV screen, and you had phosphors on there. And whether they turned the beam on or off would give you bright light or no light. And so the amount of electrons hitting your TV screen would give you the bright pixels or no pixels. And then left and right, you had a scan speed. And it would go down fast enough. You can kind of see this. This is an animated GIF of a television. You see it starts to kind of fade and go down. And so it fades, and then they start drawing another row. And so those are your frame rates, 30 per second or 29.9 something frames per second. It could raster the whole screen that fast, that many times a second. And I was the pro in my house for the vertical hold. If this got loose, then the screen would kind of jump up and down. Did anybody ever see anything like that? I don't think. Yeah. So, and that would say, Darren, fix it. And there was a little vertical hold knob in the back. It was like the beginning of my science career, probably. I was probably in elementary school. Plus, he wanted me to get up and not him. I know now. But I'm back there and I'm adjusting it, looking, and then it would stop the image, and everything was good. And it was just the electronics got out of sync, and it was not synced, and our picture was running up and down. And so then there was also a horizontal hold too. What's that? No, there was two knobs. I found the knobs. I was like, oh, look at this. I can make it go crazy. Yeah, I was probably the reason it was messing up. Yeah. So this we can do the same thing with the electron beam in the microscope. This is called rastering. Okay, R-A-S-T-E-R. Now, let's say you got a big old crystal here. Let me draw a crystal. Okay. So we're going along with the electrons. We don't see anything. Then we hit that crystal, and out comes an electron. Because electrons hate each other. So we hit this electron-rich thing, and it scares off other electrons, and they scatter. It would be so fun to be able to do this with like I always want to do this with like a pressure washer and like bucket of water or something like that, and you spray the pressure washer along, and the water that bounces off the surface ends up in the bucket or not. Okay, and if you could measure how much water gets in the bucket and plot that versus coordinate, you would do this exact same thing. So we are just pressure washing the surface with electrons in a pattern and keeping track of where we're spraying. And then we've got a bucket, and the electrons that hit the bucket, we count. And so when we hit something that has lots of electrons, we get a big count. Or when the angle's just right, we get a big count. And when we hit something, the electrons go a different direction, we don't get much count. And so we get a black and white image. Spraying the electrons on the surface, we catch them in a particular spot, and we just count the angle, that we count XY and how many electrons at XY, and then we plot that, and we get an image. So that's how. Now, but think about what happens to the surface. We're spraying it with charged particles, so the surface can charge up. So this is a problem. We have to coat this with gold. So we're hitting it with so many electrons. Gold coating for SEM is destructive. Sometimes you might have a sample that you want to preserve, and to coat it in gold, you've changed the sample now. So you got to be a little bit careful. It can be seen as a destructive technique. Why do we coat it in gold? Because we're spraying it with charged particles. We don't want the surface to charge up. Because if you've now got a charged surface and I'm sending more electrons to it trying to image, it gets steered a little bit. So it's coming at a charged surface, which now the surface is acting like a lens too. Where our lenses were just charged rings telling where the electrons to go, and it's coming at a charged surface, and it veers off a little bit. And our image looks like we're looking at a swimming pool. Like, you go to a swimming pool, it's beautiful. Before anybody jumps in, you see the lines, the lane lines, they're perfect. That's an uncharged surface. When you get in the pool, now the ripples in the water, you look at the lines and they're all wavy. That's what your image does when your sample charges up. So you're trying to get an SEM image, you're trying to measure the dimensions of something, get a good clean image, and everything is just this way. And it's because the surface is charging. So if we coat it in gold, those electrons hit the surface, a lot of them bounce off, some of them stick, and then they get conducted onto ground, and the surface is not charged anymore. And then the next beam of electrons can hit. And so we want to turn the electron beam down as much as possible so we don't blast it too much and charge it up too much. So imaging, we want to keep the electron beam as low as possible so we get a good clean image and we don't charge the surface. But when we want to do X-rays, when we want to get X-rays out of the surface, we find a particular spot and then pressure wash, and we get X-rays out. So EDS or WDS, the spectroscopy part, we can get the elemental composition of the substance for rows 3 and greater on the periodic table from the X-rays that come out. So if we have a glass chip from a suspect and from a victim, we can look at that in SEM. Low power, we get an image. We can measure dimensions, blah, blah, blah. And then we blast it with an electron beam. Pick a square and just shoot electrons at it, and then X-rays will come out of that sample. And we can tell if it's borosilicate glass. We won't learn much about the boron, but the silicon we will get. We won't learn much about the oxygen, but if it has a trace amount of nickel or a trace amount of niobium or neodymium or whatever, all these trace elements in that glass, we're going to see. Because glass comes from sand, and was this sand from this location or that location, depending, we'll have different amounts of types of trace elements in the glass. And there's other samples that we do too, but glass is a good one for SEM X-ray analysis. Then we have ion mobility spectroscopy, which is 9:15. But let me just run through real quick. Okay, it's nothing really tricky about this. It's kind of like mass spec, but it's mobility. It's not mass spec, it's ion mobility. And I like to think of it as a dance floor, okay? So the molecules are going through to the detector, but air is coming at them, okay? So think about, I don't know, this is kind of a party situation. You want to get to the bar on the other side and there's a dance floor in the middle. Okay. And it takes you a while, doesn't it? Because you're going through this gas and you have a different size than maybe a little kid. Who do you think is going to get to the other side faster? The little kid, smaller cross section, more mobile through the crowd, and less concerned about upsetting people. Okay, so that's a different mobility, and that's all this is ion mobility through a counterflow of gas. Very fast technique, very low vacuum. You don't need a high vacuum, and very simple to do. You don't even need a high voltage source because we use a radioactive source. So we're using nickel 63 to ionize the molecules. And so this is what they use at the airports. So the explosive and drug detection equipment, they wipe your luggage, they put the little wipe in there, and they use ion mobility, and you get this signal here. So you have the number of segments, the total amplitude, the width, and so on. And you have various criteria for each of those, like for an explosive or for a drug. You have a database, and when it sees a heroin or TNT, it rings the bell and calls security. We even have these in subways, sniffing for things. Lastly is chromatography. I've talked about derivatization in before. Polar substances sit on normal columns and don't want to come out. And so if we derivatize those acids with these substances here, here's 3 examples of things that would react with acids. Like this chloride would react with drugs and fatty acids and would put this thing on to the acid group. And so now it's much less polar, and it's going to come out sooner. The best one, I think, are those that contain silicon, because you got organic molecules that come out, and then you got this silicon thing, and it's going to be unique and easy to track with mass spec, because silicon has a particular isotope pattern. So after you derivatize it with the silicon-containing substances, you're going to have a great thumbprint in the mass spec from silicon. And then here's all the different techniques in the notes about different kinds of chromatography. We have huge molecules here, 10 to the 5th grams per mole, and then the smaller stuff, adsorption, ion exchange, normal and reverse partition chromatography. So this was a nice guide. I pulled it from a different book, but it's pretty cool. So thanks for letting me go over it.